So let's continue with chapter 3. And so last time we talked about this parity symmetry. So the parity is a very important symmetry in quantum mechanics. It really takes this mirror reflection of a wave function when we apply this parity operation. So the problem is that when we perform such a parity operation, so whether this psi minus x goes back to the psi of x, so that's the question, right? And for some problems, we'll see in just a moment, these properties are nicely obeyed. But for some other problems where the parity symmetry is not present, then this is not the same as psi minus x, is not the same as psi of x. So it really depends on the problem. So let's just look at these conditions. We want to ask what conditions that we can find for an even odd eigenfunctions will remain still the even odd always all the time. So under what conditions? Okay, so if I have a even eigenfunction, so I can write down this eigenvalue problem for this even eigenstate and also for the odd eigenvalue equations. So they are independent and they are decoupled. So this even eigenfunction will not mix up with the odd and vice versa. So even remains even all the time and odd remains odd all the time. Okay, so under what conditions can we have such a situation? Well, the answer is that there are two conditions that we need to satisfy in order to have the decoupled even odd eigenfunctions. The first condition is that the parity operator is not an explicitly time-dependent function, meaning the partial time derivative of the parity operator vanishes. The second condition is that the parity operator commutes with the Hamiltonian. So definition of the commutator is this pH minus HP. So we will see in just a moment that this condition is equivalent to say that the Hamiltonian shows such a parity symmetry, meaning Hamiltonian as function of x is actually symmetrical with respect to x goes to minus x. Or because we know that kinetic energy is always parity symmetric, so the only thing that could go parity violation is the potential term. So when we have such a parity symmetric Hamiltonian, it implies that the potential term must be parity symmetric. And this is exactly what we had before, because in a one-dimensional potential box, so we could shift our origin to the center of the box so that the potential term is actually symmetrical against the this y-axis in the middle, so that this v of x is actually the same as v of minus x. So oftentimes in quantum mechanics we have potential profile which shows such a symmetry, nice symmetry. So when we have such a symmetry, and we always end up with this separated even odd eigenstates like this. Okay, so let's just prove these conditions. So first, let's just write down these Schrödinger equations, the four time-dependent Schrödinger equations, like this first equation. And then the second one is that when we apply this parity operator on both sides of the equation, what we will get. So that I could just simply move this parity inside this time derivative, the partial time derivative, so that I could actually get the p acting on this psi inside this time derivative. But when I do so, I assume that there's no explicit time dependence for this parity operator. Okay, so if we have the non-zero partial time derivatives parity, then we cannot do such a shifting of the operator. But oftentimes this parity operator is a time-independent operator. So we are okay to do so. So on the right-hand side, we can actually show that if this p commutes with h, Hamiltonian, I can simply just switch the order between pH and HP. So the purpose of doing this is the following. Suppose I could have these two conditions satisfied, then I could write down the first equation and the reformulation of the second equation, which is this object P acting on psi as a new wave function, which satisfies this Schrödinger equation like this. So you can see that this, I should actually mark this P psi as a new wave functions. And these two equations are satisfied simultaneously. So I can simply just make a linear combinations of these two equations. I could just take the sum of the two divided by 2. I got 1 plus the parity acting on psi divided by 2. Or I could just subtract 1 from the other. I could get 1 minus parity operator divided by 2 acting on psi. So this is 1 plus minus 2 divided by 2. But if I do so, then I could immediately see that the right-hand side of the equation is the same as that 1 plus minus parity divided by 2 acting on psi. What is this? Well, this is nothing but the even-odd parity eigenfunctions that we defined already last time, right? Okay, because this is psi of x plus or minus psi of minus x divided by 2. So then we could actually express these two eigenvalue equations or Schrödinger equations in an independent way. Meaning I have two set of equations which are decoupled completely, because for the plus or even component, this psi even, psi plus are the solutions from this upper equation, but the minus sign, psi minus or odd component, satisfies the odd component of the Schrödinger equation. So even odd eigenfunctions are satisfy Schrödinger equations independently and separately. Therefore, the time evolution of psi plus, psi even, and psi odd are completely decoupled. So psi even would not time evolve into psi odd and vice versa. So let's just look at this condition that this parity symmetry is present, and let's look at this consequence of this vanishing of the commutator between the parity and Hamiltonian. So this tells us that if I apply this operation onto any Schrödinger wave function, the eigenfunctions, I get h of x. After the first operation, I get psi of minus x. But if this psi of x is the same as h of minus x, meaning if the Hamiltonian shows parity symmetry, then I could simply just, this is a big if. We don't know that yet, but assuming that h of x is the same as h of minus x, then I could simply just rewrite this as h of minus x, psi of minus x. Okay, what is this? Well, this is nothing but the eigenenergy times the eigenfunction. All right? Good. So let's just look at the other order. So if I apply this Hamiltonian operator first before the parity operation, then I should get this parity acting on what? This is eigenenergy times eigenfunction, which is capital E, which is just a constant, right? And you simply just add this parity onto this psi of x, you get psi of minus x. Check. So, which means that if the Hamiltonian has a parity symmetry, then we can show that this parity and Hamiltonian actually commute. Okay, so this is the whole purpose of this derivation and proof that the condition that we can decouple this even odd eigenfunctions is that the Hamiltonian itself is parity symmetric. But what does that mean? We know that this Hamiltonian is actually p squared over 2m plus the potential term. And what is this? This is second derivative respect to x, which is the meaning of this momentum squared plus the potential v of x. But we know that if we change x to minus x, this doesn't affect this second derivative's wave function with respect to x, because this is the same, right? So if you change x to minus x, and the second spatial derivative, the x squared, doesn't change, right? So the only thing that we need to satisfy in order to satisfy this parity symmetric condition is that v of x is the same as v of minus x. Okay, so we complete the circle, and we successfully show that if we have such a condition satisfied, and we know for sure that the eigenstates could be decomposed into two different parts, namely the even parity symmetric eigenfunction and odd parity symmetric eigenfunction. But what is this condition is telling us? Well, this tells us that this potential term should have such a mirror symmetry. But this does not occur always, because you can imagine that in many different quantum mechanical problems, this potential term may or may not show such a parity symmetry. For example, the easiest example is that if I have this very strange shape of this potential, like this red, then we could see very clearly that this potential bounded by the red is not mirror symmetric, because there's a missing piece right here. Okay, so if I make the mirror symmetry, this potential profile on the right in this missing area will not match that on the left. Okay, so in such case, we don't have such a symmetry. In other words, if we don't have such a mirror symmetric potential, then the even function and odd functions are not decoupled anymore. Okay, so as time evolves, the even parity eigenstates would actually involve the odd, or the eigenstates are mixtures between even odd symmetric functions. Okay, so in other words, the even odd will not be decoupled anymore if we don't have such a mirror symmetric potential. So this is a simple but very important lesson we learned today, that in order to have such a very beautiful, say, decoupled even odd eigenstates, we need a mirror symmetric potential. Is everyone okay? This is straightforward derivation. Great. So let's take a short break. When we come back, I would like to make some remark regarding how to distinguish the degenerate eigenstates. Okay, so let me make a final remark regarding the commutator and degenerate eigenfunctions that we discussed last time. Last time we mentioned that there are degenerate eigenstates in quantum mechanics. For example, the free particle And you know that there are two degenerate eigenstates describing the particle moving to the right and also to the left. So they are described by this psi plus minus plane wave as their eigenstates. And these so-called right-moving, left-moving free particles carry flux plus or minus c squared times velocity, as we already mentioned last time. But how do we distinguish these two? Well, we could distinguish these two degenerate eigenfunctions by another operator which commutes with Hamiltonian, meaning this Hamiltonian could either commute with the momentum operator or the parity operator. So let's look at this first example, that the free particle in the box, or this psi plus minus eigenstates, and we could distinguish whether this particle is moving to the right or to the left by applying the momentum operator. Remember that. If we apply the momentum operator acting on this psi plus minus, we'll get the eigenvalue plus or minus p, right? So if we measure this momentum of this right-moving flux or left-moving flux, we'll get two different results. One is plus, another is minus p, right? But the reason why we can do this is because the momentum operator commutes with Hamiltonian, because Hamiltonian is simply just a free particle, so it doesn't have the potential term. It just has this kinetic energy. So the kinetic energy is what? It's p momentum squared, right? So of course this momentum operator commutes with momentum operator square. So it is because of this variation of the commutator between the momentum operator and the Hamiltonian that saves the argument, right? So that allows us to really detect the difference between these two degenerate states, because otherwise these two degenerate states are having the same eigenenergy. Okay, so this is just one example. And the second example is precisely the parity. So suppose the eigenstates are characterized by the even and odd eigenfunction, like this cosine sine. And again, so they are degenerate, for example. And how do we distinguish these two? Well, of course, we could distinguish by their parity, right? So because the parity acting on this cosine and sine will lead to two different results. For cosine, it doesn't change sine. For sine, it changes sine. But the reason why we could do this is precisely because the parity operator commutes with the Hamiltonian. And that is precisely because the reason that I just mentioned, that because the potential energy does show the mirror symmetry, so that this Hamiltonian is mirror symmetric, so it has the parity symmetry. As a result, the parity operator commutes with Hamiltonian. Okay, there is a big but. But in many cases, if Hamiltonian commutes with some operator A, and the Hamiltonian commutes with another operator B, however, A and B do not necessarily commute. So in other words, A and H commutes and B and H commutes. It doesn't necessarily imply that A and B commute. We need to prove this. Okay? And a very important and simple example is precisely the parity and momentum operator. Remember, Hamiltonian commutes with the momentum operator, and Hamiltonian commutes with the parity. For simple examples, but we'll show that the momentum operator does not commute with the parity. So let's prove it. So let's just look at this two different operations in different orders. Right, suppose I apply parity first and then momentum operator later. So after the first operation, so the parity operated on this psi of x gives you psi minus x, right? And the momentum operator acting on psi minus x leads to such results where this partial x derivatives with respect to this wave function psi of minus x. Okay, so that's just the first operation. The second is the opposite way around, that you apply the momentum operator first and then later parity, which gives you plus RH bar d by dx psi of minus x. So if you do the other way around, you first apply this momentum operator acting on this psi of x, it gives the minus h bar d by dx psi of x. And then you apply the parity. When the parity applies, it applies all these functions of x, which means that you need to flip the sign of this x in the partial derivative to minus x. You need to flip the sign of the x inside the argument of the psi, which is psi minus x. And when you have this actual minus sign, this will cancel another prefactor minus psi, and you get plus IH bar. And by the first operation, you get minus H bar, the same quantity. So of course, they are not the same. So this is a very important and simple exercise telling you that these commutation relations are very important, and we need to really prove each of these commutator, and we do not rely on the other commutators to actually imply a third commutator. The third commutator doesn't necessarily satisfy it unless we prove it. And one more remark. We will show maybe next chapter that if we have an operator A that is not an explicit time-dependent operator, meaning this partial A partial T vanishes, and also this A commutes with the Hamiltonian, then there is a very important consequence of this result, meaning this operator A is actually a time-independent constant of motion. Meaning A operator doesn't evolve in time, because the total time derivative of a quantum mechanical operator could be decomposed in terms of partial time derivative plus this commutator between H and A. So we will prove that later, but at this stage, we just appreciate the consequence, because as we know that this parity operator satisfies these two conditions, that first, it is not a time explicit function, so this partial parity partial T vanishes. And the second, Hamiltonian commutes as a parity operator. So combining these two conditions, we immediately say that the parity is actually a constant motion, meaning it does not evolve in time, because if you take total time derivative as a parity operator, it vanishes, which means that under time evolution in quantum mechanics, the parity operator doesn't time evolve. It always stays a constant in time. So this relation doesn't just hold for a parity operator, it holds for all the quantum mechanical operators. So as we'll see later, that the A operator could be, say, angular momentum operator, or spin angular momentum, or whatever operator that interests us. So all the quantum mechanical operator, if this operator satisfies this condition, then this is a constant motion. Okay, so namely, there must be a conservation laws associated with this constant motion. So it is the end of the chapter 3. In this chapter, we introduce very important concept, this parity symmetry and simultaneous eigenstates, and also the commutator between the Hamiltonian and certain operators. So these ideas and simple calculations will come back again. Let's start chapter 4. Some of you may have already learned how to solve the Schrödinger equations for a particular, say, potential in one dimension. So I will go quickly. I assume that you know many of these details, but I would like to highlight important physics related to the quantum mechanics, the heart of this quantum mechanics. So for example, negative energy states and quantum tunneling, and how to detect particle inside the barrier, and so on. Okay, so these concepts are really counterintuitive, and all of them are related to the Heisenberg uncertainty relation. But I think this will be my highlight, and I'll leave some of the calculations to you as an exercise. As I mentioned in the beginning of the course, this course is not about the quantum physics, it's about quantum mechanics. So we will start the very idea of this quantum mechanics, namely the operator method and Dirac notations, and broad cascades of Dirac representation of quantum mechanics, and some of the linear algebra associated with the Dirac operator. So that's the idea. Let's just look at, in this chapter, our textbook listed quite a number of one-dimensional potential that we could solve analytically very easily. For example, this potential steps and potential well and potential barrier, and also harmonic oscillator potentials. These are these fundamental one-dimensional potentials that we could solve by solving the Schrödinger equations easily. So there are many new physics that can be learned from solving these potentials. So let me just highlight two important physics. One thing is so-called quantum tunneling. Meaning, if we have a potential bump like this, and I could actually send a particle to hit this potential barrier, classically, if we have such a potential that has a higher energy than your particle energy, then the particle can only bounce back, and the particle can never tunnel through this barrier. But quantum mechanically, there is a finite probability that allows the quantum particle to tunnel through this potential barrier like this, where this energy of the incoming particle is actually smaller than the height of the potential barrier, which we call this classically forbidden region. So in classical mechanics, this is forbidden. But quantum mechanically, it is not forbidden. So how to really understand this quantum tunneling is not an easy task, because the most difficult, challenging question is this: how do you know that the particle ever tunnel inside the barrier? How can you detect the particle if this particle has ever been trapped inside the barrier? And how do you know that this particle that tunnels through this barrier really comes from the particle that tunnels through the barrier? So I will try to convince you that quantum mechanically it is counterintuitive, but it is not logically wrong. And the reason why we have such a counterintuitive result is precisely because the nature of quantum mechanics, namely the particle-wave duality and Heisenberg uncertainty relations. So these two are the fundamental principles of quantum mechanics that I emphasize many, many times in the past, and these principles will come back when we discuss quantum tunneling. You need these two principles to understand what is going on here. And another important new concept is so-called quantum bound state. So inside the potential well, if the well is actually deep enough, and this potential well can support so-called bound states. So those bound states are the states that are bounded by this potential well, and these states are there, and they cannot easily get out of the trap. And in some cases, we have such a bound state, and in other cases, we don't have the minimum requirement to support the bound state. Okay, so the bound states are very important quantum states that could explain many stable, complicated quantum objects such as molecules and some complicated chemical compositions that you learn from the chemistry. So many stable quantum states are bound states, and we will learn the essence of bound states. And another equally important concept is the finite ground state energy, or zero-point energy. So, for example, in the harmonic oscillator problem, like this, we'll show that the lowest energy state, or the ground state, has energy that is larger than 0, which means that the ground state energy is not zero energy state. So this probably arises already in the earlier example of the particle in the box. So remember that in the example of the particle in the box, we have more or less the same situation where the ground state energy, we call this E1, is what 2m a squared h bar squared pi squared n squared, where n is 1. Meaning the ground state energy is not zero energy state. So how come? Again, the reason why we have such a positive energy ground state is that, again, it's tied to the condition or the principle of the Heisenberg uncertainty relations. So because of the Heisenberg uncertainty relations, the ground state energy is not a zero energy state, shows a positive energy. And from this simple particle in the box example, we know that in the ground state, the average of the momentum vanishes, but the average of the p squared does not vanish, which means that at ground state, the particle is still in motion, namely the particle carries kinetic energy and also the momentum, but on average the momentum just cancelled, but the kinetic energy survives. So we will look at this problem one more time when we get there. So how do we understand this important consequence of this finite ground state energy? So we can only make sense of it by Heisenberg uncertainty relation. Because of this, we can argue and show that the minimum energy of the system has to be greater than the E1 or equal to E1. So we will get that later. Let's continue. So we first look at this easiest example of a one-dimensional potential step. So the potential V of x shows such a step like behavior. So it vanishes when x is negative, and it is a constant positive value, and for x positive. So there is a jump right at x equals 0 from 0 to the finite value v0. So imagine you have a quantum particle that will hit this potential step, and it could get reflected, and also it could actually pass through this potential step depending on the energy of your incoming particle, right? So the energy, capital E, could be either smaller than V0 or larger than V0. So then we could just write down this time-independent Schrodinger equation like this and rearrange this Schrodinger equations in a more convenient way so that this u of x is the function that we need to solve. And then we could define two quantities, k and q, where k squared is defined as 2m capital E divided by h bar squared, and q squared is this 2m times E minus V0, the difference between the energy of the incoming particle and the potential step divided by h bar squared. So let's just look at these two cases. The first case, when x is negative, we know that the potential vanishes, and in that region you may have just incoming plane wave and also reflected particle with a coefficient capital R. So in this case, we could actually try to find out what this capital R is. Of course, for the positive region, x positive, this wave function on the positive side can be written in terms of exponential factor e to the iq times x, where the q is defined as the square root of this quantity right here. So you can see very clearly that the q could be either real or purely imaginary. So if capital E, your incoming energy, is actually larger than your V0, meaning very high above this potential step, higher than the potential step, and the particle can actually travel freely to the other side. So this q is a real number. And then the other side of this potential, the particle is actually a plane wave-like solution with the proper coefficient t, which is the transmission coefficient. However, if the incoming energy is actually lower than the V0, like this, then we could still have some solutions on the other side, on the positive side of the potential step, but this q is actually purely imaginary, meaning this solution is actually exponential decay. Okay, so you could we'll see that in just a moment, that if you have such a low energy incoming particle, then on the other side of the potential step, this wave function actually decays exponentially. But if the incoming energy of a particle is actually larger than the step, then you could easily tunnel through the other side. So we have these two different regions with two different solutions, possible solutions, and the problem is what is the so-called reflection coefficient and the transmission coefficient. So we need to solve for capital R and capital T, and both capital R and capital T can be real numbers or complex numbers. So to really solve for this R and T, we need several conditions. The first one is called conservation of flux, meaning whatever flux that you find on the left side of the potential should actually match the flux on the right. Right at this x equals 0, these two flux of particles must conserve. So this is precisely the condition that we mentioned last time, that although this free particle wave function is a plane wave, which is not square integrable, but we can still really follow this particle by calculating the flux of the particle passing through any cross-section area, so that we could actually count how many particles that pass through this particular area, and we should make sure that this particle flux is conserved everywhere. Because it's not physical to really think about the situation where the particle flux is missing out of nowhere. So we cannot have extra particle flux injection out of the blue, or we cannot miss any particle flux for no reason. So the particle flux must be conserved, because this is a conservation of particle number. And as we already mentioned, that we are able to calculate the flux for the simple cases. As a result, we are able to actually match this particle flux on two sides of the potential, and we demand that this particle flux must be conserved right at the boundary. So this is the first condition. And the second is the wave function should be continuous, which means that the wave function that we find on two sides of the potential must match right at the boundary. So this is because the probability of finding the particle must be conserved. Conservation of probability. So we know that this Schrödinger wave function represents the probability amplitude of finding a particle any place in x-axis. So this probability must be conserved. In other words, we cannot say that on the left side of this potential step, this probability is actually, say, P1. But right next to this potential on the right side of this step, we have different probability. So if these two probability are not the same, and we have a trouble. Because right at the boundary, there's just one unique probability that we can find this particle. So we cannot have two probabilities at any place in x-axis that we claim that we can find this particle at different probabilities. As a result, since this probability must be conserved right at the boundary, so the wave function itself must also conserve. Meaning, this wave function must be continuous right at the boundary. And number three, the first derivative of this wave function psi respect to x is also continuous at the boundary. So not only this wave function itself is continuous, but the first spatial derivative of psi is also continuous. So remember, the first spatial derivative of psi represents the velocity or momentum of your quantum particle, right, h bar k. So this tells us that this momentum must be continuous or must be conserved, which says that the momentum of the quantum particle must be continuous right at the boundary, because momentum has to be conserved everywhere. So that we should demand that at the boundary, the two solutions that give you two different slope or derivative or momentum, and these two momentum must be the same right at the boundary. Okay, so we listed three conditions that allows us to use as a weapons to find out this capital R and capital T at two different regions. So now I think we are in a position to really figure that out. We'll just list all those three different boundary conditions, and then we could actually figure out these two coefficients. Let's just list all these three conditions. The first one is the flux conservation. So as I mentioned, this flux is two sides of the potential step must conserve right at the boundary. So let's just compute the flux on the left-hand side of this potential step. We follow this standard definition of the flux that we defined earlier, and plug in the solutions of this U, which is, in general, the combinations of the incoming plane wave and the reflected plane wave, right? So incoming on the right and the reflected to the left. And you get immediately this combination, which is h bar k over m times 1 minus a square magnitude of this capital R. But we could very easily just separate these two different fluxes by a simple consideration, namely, we know very well that this incoming plane wave carry this flux h bar k over m that we already calculated for a free particle. So this h bar k is the momentum, and m in the denominator is the mass, so the momentum divided mass is nothing but velocity. And the prefactor of this incoming plane wave is actually 1, so that this density is actually 1, so you get the flux, total flux h bar k over m. So you don't need to really calculate this complicated object by just looking at this plane wave, and you know immediately that it carries flux h bar k over m. So likewise, the reflected wave carry the negative flux because it goes the other way, opposite direction, from the right to the left. So it should carry minus h bar k over m times square of the prefactor. Remember, this is the density of your particle. So capital R squared refers to the density of a particle moving to the left, and you should multiply this by this h bar k over m and carry minus sign. So you add these two flux together, you get a total flux. Okay, so this is easy. What about the right-hand side of this potential step? Well, your U is actually transmission coefficient times e to the iqx. So of course, you need to assume that your energy, E, is actually larger than your potential step, V0. So that is outgoing transmitted wave is a wave. It's not exponential decay. So in such a case, you can very easily see that on the right, you get the flux of this h bar q divided by m times t squared. So these two quantities must agree right at the boundary. So you immediately get the relation between R and T from the flux conservation. So second, from this boundary conditions of psi of x, which is continuous right at the boundary, so you could immediately see that just plugging this x equals 0 on both sides of solutions, and you get agreement at the boundary, so which means that 1 plus R must be equal to T. And number 3, that the first derivative psi with respect to x must be continuous at the boundary. So you will immediately see this condition. You just take the differentiation of psi with respect to x on both sides of the potential step and make it equal right at equals 0, and you get the third condition. So from the three conditions, you can easily solve for R and T. So this is the solution, and you could check whether they satisfy this flux conservation. So you can simply just plug in this value of the capital R and capital T back to this flux conservation, and you immediately see that you could satisfy this flux conservation. So the problem is almost solved. However, there's a twist. So this is just a simple algebraic equations that you need to satisfy the three conditions, and you can easily check the solution. But of course, to get the solution, we sort of assume that this incoming energy, capital E, is actually larger than V0. So we will come on this in just a second. So let's just make some remarks. The first one is that in classical mechanics, the particle actually goes over a step. It could slow down, but it never gets reflected. So this is a very important point. Imagine that the energy of particle, capital E, is actually larger than this V0, so the particle actually passed through this potential step to the other side. But imagine this is a classical object, like a baseball. So if you throw a baseball up the hill like this step, then this baseball simply just goes through the step without being reflected. However, in quantum mechanics, there is a probability, capital R, for this quantum particle to get reflected. So the fact that we have certain probabilities of being reflected for a quantum particle to hit this potential step, it is a consequence of quantum mechanics. And the reason why we get a reflected wave is because the wave nature of a quantum particle leads to the finite reflection coefficient, even the energy of an incoming particle is larger than a step. So this is highly non-trivial because in classical mechanics, you can never imagine that the particle passed through the step will go back if the energy of the particle is actually larger than the potential step. The classical object simply just passes through the step without turning back, but quantum mechanically, we allowed certain finite probability for this quantum particle as a wave existence could actually get reflected. So the reflected wave from this potential step problem is actually a consequence of the wave nature of a quantum particle. So once we can imagine that this quantum particle is in the wave nature, so we can understand why there is a finite probability of a quantum particle that can get reflected, even the energy E is actually larger than V0. So number 2 is when this energy, capital E, is actually much larger than V0, or this little q is actually goes to K minus. Then you get no reflection and total transmission. So meaning in very high energy of incoming particle, there's no reflection, which is good because this is consistent with what we can imagine in classical mechanics, namely for a very high energy incoming particle, the particle will never bounce back. So in quantum mechanics, it is also the case, but this happens only when this energy of the incoming particle is really, really high. It's much higher than the V0, so that when this is the case, the Q goes to K minus, which means that this Q is actually asymptotically close to K, which means that this K minus refers to K minus infinitesimal value called epsilon. So when K is really close to Q, this reflection coefficient really vanishes. And so when K is actually Q, denominator is actually 2 times K, the same as numerator, so they get cancelled, so T, capital T is actually 1. You get a total transmission, but no reflection. So this high energy limit really agrees with our intuition from classical mechanics. So number 3, what happened if this energy, incoming energy, capital E, is smaller than the potential step, V0? So in this case, as I mentioned, Q goes to purely imaginary. So the solution on the right side of the step goes like e to the minus the absolute value of the Q times x. So for x positive. So this is the exponential decay function, right? As I mentioned, if you have a situation where this energy is actually lower than this potential step, and on the other side, this incoming wave will actually decay exponentially. Okay, so what does that mean? Well, this means that you get a total reflection, because now you could use this general formula to simply replace Q by I times Q, right? So if you simply just replace Q by I times Q, it is also the solution in the case when energy capital E is less than V0. So this is also a solution. You can check that. Okay, so let's just take this for granted, and we plug in this square of the reflection coefficient capital R squared, and we'll get this result. Magically, this gives you 1. Okay, so this is the start of the confusion. Because you know very well that something is going to inside the step. Although it is exponential decay function, but something is actually get transmitted inside the barrier, inside the step. However, you get the total reflection because the square magnitude of the reflection coefficient is 1, meaning the magnitude of the reflection coefficient is 1. You get a total reflection. If you get a total reflection, what happens of this wave function that leaked into the step? So what happens here? What is going on? You get something that leaks into the potential step on the other side, but then you still get the total reflection. Isn't that strange? Isn't that weird? It looks like something is not conserved. Either the probability is not conserved or the flux is not conserved. Because you get a total reflection, but something is still inside on the other side. If you get a total reflection, naively you will think that nothing will be inside the potential step because you get everything already, right? On the left side of the step, so how can you get something still trapped inside? Okay, so this is the first situation where you get confused by quantum mechanics. You should get confused. So let us take a short break. When we come back, I will resolve this seemingly paradoxical or inconsistency that you naively think. So there's no breaking of any conservation laws, and it's just the nature of the quantum mechanics. So let's take a short break. So to see what's going on, you will need to simply just go back to the flux. And once I tell you this flux is still conserved, and you will immediately understand everything. So let's look at this flux on the left-hand side. So in this total reflection region, you get the J left, which is h bar k over m times 1 minus r squared. Since capital R squared is 1, so you get 1 minus 1 is actually 0. So you get 0 flux, total flux on the left, right? So what about the right flux? So you naively would think that while something is leaking inside the barrier or the step, because you have something, that something is actually exponential decay function, right? So you naively would think that there might be a flux on the right. Okay, otherwise this wave function wouldn't exist inside the step because something is trapped. We like to actually detect the flux that is trapped deeply inside the step. So what do, right? So you could simply just calculate the flux on the right, and you immediately see that this is 0. Why? It's the perfect timing to end. So this u on the right is actually a real function in x, right? So there's no imaginary complex values on the right because this is an exponential decay function, which is a real function in x. So if this u is actually a real function, what's the difference between u star and u? No difference. As a result, you get the total cancellation of these two terms when you really calculate j on the right. Therefore, you get no flux. So next time, I will make a comment on this seemingly very confusing result. You get something trapped inside the step, but there's no flux. What is going on? Something is really inside the step, but there's no flux. If you simply just take a measurement by waiting the particle to hit this area, and then you measure nothing. Okay? You get nothing because there's no flux. But this is a good sign, because on the right you get no flux, no net flux. On the left you also get no net flux, so flux is conserved. The flux is conserved, but the only thing that confuses you is that there is indeed something inside the step, but there's no flux. This is the magic of quantum mechanics. There's something inside the barrier or step, but you cannot detect them. Why is that? You will get the answer next time. Right? So think about this. Challenging and difficult and counterintuitive quantum mechanical results. There's something inside the barrier, but you don't know, because you detect no flux. So let's end of today's lectures.